We're making cuts perpendicular to the x-axis because that's our axis of rotation. So we're making cuts perpendicular to the x-axis. So we can see our cylinder, right? We're pulling out these discs, and we know the formula for every disc is pi r squared, where r is the radius of that disc. And so when we make our cut, when we make this cut, it's perpendicular to the axis of rotation. And for the disc method, our cut is just our r value, right? It's just our circle because we can see it. Our circle comes around. It comes around. It makes a circle. So that's an r value. It rotates around. It makes a circle. So when we go to set it up, what are we integrating with respect to? Do you guys get dx, right? Yeah. Integrating with respect to x. And that variable has to match your limits. So what limits do we got on there? 0 to pi? Pi r squared. But our r value is just top minus bottom, or 2 sine x minus 0. It's that distance, right? The distance between this curve and this point here. So that's 2 sine x. So the r is changing. That's why it's got the variable in it, 2 sine x. And so what you're actually integrating is from 0 to pi times 4 sine squared x dx. Would y'all agree when we square that radius, we get a 4 in there? And how do you integrate sine squared? What do we use?
Turn it into 1/2
Mm-hmm.
2x, or
Yeah.
sine 2x.
Absolutely. With even powers, we use our power reducing formula. So everybody is going to change sine squared into 1/2 1 minus cosine 2x. That is our power reducing formula. Beautiful, beautiful. And once we do that, we don't have any more powers on our sines or cosines, so we just straight up integrate, right? We just straight up integrate. But we split it up as the two parts. I'll pull that 2 out front and make that 2 pi times the integral from 0 to pi of 1 minus the cosine of 2x, and integrate each part. See if you guys are getting and matching what I'm getting. Did you get 2 pi x minus 1/2 sine 2x? And if I'm not matching you, let me know. That's 2 pi times pi minus 1/2 sine of 2 pi minus 0 plus 1/2 sine of 0. Two pi and 0 are both coterminal angles. They start and stop at the same place. 0 degrees doesn't have any measurement. 2 pi goes off. 0 degrees doesn't have any measurement. 2 pi goes all the way around the circle. But they share the same sine and cosine value. It's right here, right? Two coterminal angles right there. The cosine is the first coordinate. The sine is the second. Sine of 2 pi is just 0. Cosine of 0 is also just 0. I get 2 pi times pi. I get a weird answer of 2 pi squared cubic units. Is that what you guys are getting? Who's got questions? Does anybody have a question? Yeah, go ahead, Jaden.
On the test, if I just wrote 2 pi times pi minus 1/2 sine 2 pi subtracted by 0 plus 1/2 sine times 0, would that be right?
I will not take off. I will not take off, but I expect you to know. Yeah,
Okay.
I won't take off. I expect you to know that, though. I don't know about Professor McDevitt in the next class, okay? So good practice up with me. Yeah. AK, go ahead. Question.
So it's a top and a bottom when we rotate.
Correct.
So I wanted to ask, if it's wrong to do 2 sine x minus negative 2?
Good question. Good question. If you're rotating around the x-axis, the pi r squared gives you the full circle, so there's no need to do both of them. The fact that we are integrating circles. See, remember, we're doing, let me slow it down a second. We are integrating the surface, we're integrating areas, and each of these areas, whether it be a semicircle or a rectangle or a triangle, each of these semicircles has a little bit of thickness to it. Right? So we have a napkin. Has a itty-bitty amount of thickness to it. I mean, if you opened up a napkin and laid it out, they're like almost see-through, right? But it has itty-bitty thickness to it. But if you stack them all up, you get a big volume, right? So the idea is, with these circles, we have an area. And the beauty of the circle versus a semicircle, we're not putting semicircles. The beauty of the circle method is pi r squared captures both the top and the bottom. So we don't have to worry about the bottom curve right now. Now, yeah, does that help a little bit? Yeah. Gavin.
Could you like split up your sine to double angle theory, or because it's 2x, so you could
You could right here make it 2 sine x, 2 cosine x. Absolutely, I could. But because I don't, yes, I could. Yes, I could. But for me, because all I'm doing is plugging a limit in versus rewriting a triangle and using the triangle to get information.
So it's not necessary.
It's not necessary to split it up. Correct.
Define
Nope, you can just plug it right in. Yep. Any other questions? Grant?
I know this is really small, but you have negative 0, 0 plus 1/2 sine 0.
Yep.
Shouldn't it be 0 minus 1/2?
Well, because we take top minus bottom.
Oh, it half's negative. Never mind.
Any other questions? Alrighty. That's our first warm-up. I'm going to put a big smiley. I'm going to make it a yellow smiley so everybody sees Tina really, really, really likes this problem. Oh, yeah. I really like these problems. Problems that I like, you're going to see again, whether it be on a final or an exam, but I like this problem. Maybe it's a cosine or a sine. Maybe it's a little different shifted or something like that, but I really like these problems because they challenge us to work with trig functions. They challenge us to do a method where we have to do integration techniques, so I like these problems. As my second warm-up, what if I take the same shape, so same region, it's bounded by y equal 2 sine x, where 0 is less than or equal to x is less than or equal to pi, and it's bounded by y equals 0. So I'm going to take that same region, but I go about the line, I rotate it about the line y equals 3. Gives us an entirely different shape, right? Can you kind of picture what's happening here? It's kind of like a spool of thread, almost like filled spool of thread. I don't know if you've ever exaggerated, right? A spool of thread, like with the thread wrapped around it and whatever. But it's got this. Well, actually, it's hole in the middle. It's got a hole in the middle, right? So you got this cylinder, but it's drilled through the middle. It's got this funky drill hole through the middle of it. I just want you to set it up. I don't want you to evaluate it out. I just want the setup on this. But we know right away we have a hole, right? And when you have a hole and you're thinking about discs, it actually becomes a washer, right? Because when I cut it, that disc forms a washer. We've got a hole in the middle, right? So a hole causes us, using the disc method, to become a washer. So what we're doing is we're adding up the areas of washers, and so we know our formula is going to be pi big R square minus pi little r square, where big R and little r are the outer radius and the inner radius for that washer. That's the cross section. Now I am going to put a little note, R, big R and little r are both measured from the axis of rotation. So I'm going to let you guys label those and get me a setup. Label those and get me a setup, okay? Label those and get me a setup. What is your big R? What is your little r? And I am, on your test, going to give you a picture. Or either give you the graph or have you graph it. I'll probably give you the graph, okay? And then I'll say, use a disc method, rotate it about this line, or use a washer method, rotate about this line. Label big R, little r for me. Do you see what I'm saying? Like I'm going to say, label this big R, little r. Label this little r, okay? Label this H and R for our cylindrical shell method. Draw your cut and label that, okay? So I'm going to have you actually show me that on your test. I'm going to tell everybody that now, okay? To the outside, little distance goes to the inside. Big distance goes to the outside, little distance goes to the inside. So when we go to set this up, big R measures a distance. It measures the distance top to bottom, right? Top to bottom. So what is that distance for big R? What did you guys get? 3 minus 0, or just 3, right? 3 units. It's always constant. It's always 3 minus 0, or 3 units. Little r, top function minus bottom function, right? So that's 3 minus 2 sine x, right? It's the distance between those two curves. 3, which is constant, and 2 sine x, and that gives us that inner radius. It's changing, right? It gets small and then it gets big, and that's why it's got this variable in it, whereas the other radius was always constant. Yes?
On the lecture yesterday, Wednesday, you had sine minus 3 minus
Did I go about a line y equals 1? So if that, or negative 1, I think I went around a different line, unless I messed up for you. Because you were going around this one over here, so it was right function minus left function. This one is top function minus bottom function, do you see? Good. And I apologize yesterday for lab. I know that if you were in the second lab, it was utter chaos. Okay, we were all at the board and it was crazy. It was just too crazy. I'll never do that again. My first class was controlled chaos, my first lab, but that second one, so don't worry, I won't ever put you in that kind of a situation again. That was a little bit way too much over the top, but. Pardon?
I like the whiteboards.
I'm going to do whiteboard work. I absolutely am, but I think I'll put you in smaller groups and take turns doing writing versus having 27 people all around. That was a little difficult to manage. So, yeah. All right, guys, so here we go. Did you guys get an integral for me? We're integrating with respect to x because we're cutting perpendicular to the x-axis. You guys have 0 to pi, so the limits stay the same, right? And then it's pi big R squared minus pi little r squared. So when you set it up, hopefully you guys are getting pi times big R squared, which is 3 squared, minus pi times little r squared, which is 3 minus 2 sine x squared dx. Does anybody have any questions on that setup? I don't want to work it out right now because we have a lot to talk about.